The video, the lecture video of linear least squares is one of the estimation methods we discuss in in system identification. We start with this method because first it's simple. It's a very mature, well-established method. You can just call library. There's a lot of tools that can allow you to solve practical problems using the linear least square. So in this video clip, we're gonna start with the definition so that you get to know what linear regression or linear least square is. We give you some applications in engineering, and we jump to explaining the method and how to solve it numerically. I mean, how to solve it analytically first, because when you get the analytical form of the linear least square solution, it will allow you to further discuss about its statistical property. But we're going to keep that topic, for the last. And then, we will show you how to numerically compute it, so that you know that all the libraries or the package, in the market, solve it based on the method. And then we give you an extension of least squares, which is called weighted linear least squares. Linear regression, this problem, the model start with the establishing a linear relationship between the variable y, or the output variable, with the variable x using a linear function. In this equation, you will see the variable y that we assume it to be the measurements. It is called the response, the regressed variable, the explained, the dependent variable, because your focus is on the variable y, but you're looking to get a list of xk. These xk are the input variables. You believe that all these xk's can be used to explain y. It's like they are influential variables to the response of y. And in principle, you can assume that there are n predictors, n input. So there are several names for x: predictor, explanatory, independent variables. For example, you believe that solar power generated from a solar cell can be explained from solar radiation, solar irradiance. It depends on how much radiations in the atmosphere at a given time at a given place. Okay, and probably there are some other factors. For example, it depends on the temperature of the solar cell. Okay. Whenever you assume a linear relationship between y and x, okay, this is what we call, you are going to use a linear regression model. And the problem objective is, of course, when you come up with this model, you want to determine the coefficients beta k, because each beta k can tell you the amount of the inference from xk to y. Beta is called the regression coefficient. The equation that you saw previously, of course, you can write it into a vector form. You can write it as x transpose beta, where beta is coefficient vector, x is the variable, x is the predictor. But then think about in applications, this is a model. You take a look at this equation as a equation of where you leave y and x arbitrary. But when it comes to applications, you're going to have measurements, a lot of measurements between y and x. Think about what I just said before. you have a solar cell. And then you can have, of course, you're going to have a sensor, all right, that the sensor that you can collect the measurements of generated power. You can have a weather sensor where you can, of course, sense the solar radiation and the temperature. Of course, at various times, at various days, you're going to have a bunch of these measurements. We have a bunch of these measurements. So when you repeat this regression equation, you repeat with the index i's. Okay, take a look at this equation. Now I'm gonna, so with the yellow color, it means that you're gonna repeat with the 1, 2, 3, dot, 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 until m measurements. Okay, so with the index, with the pink color, it means that you collect x1, right? You collect x1. So the yellow color, it means that the variable x1 for sample index 1, 2, 3, dot, 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 m. Okay, so in this form, when you collect the m measurements, you can form a linear regression containing the measurements into a vector form, y equals big X times beta. Now, not to be confused between these y and these y, you just look at the context. Okay, when I use this equation, it means that, okay, this is a linear model equation. Okay, it's just used to explain the relationship. It explained that, oh, you're gonna have x1 until xn variable. Okay, but when it forms into a matrix form, so please be reminded this vector y, which is small vector y, actually contains the measurements of the variable y. Okay, the matrix X here is often called the design or the regressor matrix. Sometimes it's called sensor matrix because the matrix X here contains the measurements of the input variables, the predictor variables. Okay, and so the problem setting is the following. You are given the vector y, the matrix big X, and you want to, of course, you want to solve this equation for beta. If you get beta, if you have beta, of course, in the future, when you observe new X, new predictor variables, for example, if you can predict, all right, if you have the measurements, if you have the values of solar irradiance and temperature at another time, and so that you can predict how much power would be generated from the solar cell. Okay, so the whole point is to get to estimate beta, because when you get beta, you can get an estimate of y. Then you'd see that here is a linear equation. Okay, from this slide, how many equations, how many variables? If you look at this notation, Toto, can you answer that?
There is m equation with n variable.
Yes, very good. M equations, n variables. You see that this is a rectangular system. It doesn't have to be square. So m is the number of measurements. All right. We're going to see later that in terms of estimation, you would prefer to use more data. Okay. More data will allow you to get a better estimate. Okay, I leave the statement here for now, but we will see the supporting reason later. So when m, so usually we end up with, the case of a tall system, because you tend to have more equations than variables. Okay, that is called overdetermined linear equation. So when you solve over-determined linear equation, the exact solution does not usually exist, because we know that when you have a linear system, the condition for the solution existence is that y has to be in the range of x, and when x is tall, this condition may be hard to may be difficult to satisfy. Okay, so that's why it comes to this lecture. We're gonna instead of solving over-determined linear equation, we're gonna find beta in a linear least square sense. Okay, so the problem statement of the linear least square formulation is the following. Okay, whenever you have over-determined linear equation, okay, m is bigger than n, instead of looking for an exact solution, you take a look at the residual r, which is y minus x beta. R is going to be a vector of m by 1. Okay, and of course, because you cannot get the exact solution, the residual vector is non-zero, so you want the residual vector r to be as small as you want, as small as possible. But then how can you measure the size, the magnitude of this residual vector? Then you use the concept of two norm. Okay, you use the two norm to measure the residual error, and then you choose beta to minimize it. So when we break out the expression of the two norm is this, all right? Another way to look at this is y minus x beta is going to be y1, y2, dot, 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 ym minus x1 transpose beta, x2 transpose beta, and so on. All right. My x, the regressor matrix, can be partitioned into rows. All right. All right. So so the two norm is gonna be the square root, the sum of I from 1 to m, yi minus xi transpose beta square. Okay. The solution that is returned from this equation, from this problem, is called the least square solutions, and it's the same as minimizing the two norm square. Minimize the two norm and minimizing the two norm square give the same solution beta. It's just the objective functions of two problems are, squared of one another. Okay, let's take a look at some examples first. So this is the advertising data set from Introduction to Statistical Learning textbook. All right, it's a famous data set. So you have a product sales. For example, you run a company and you have a product. All right, and of course, you have the records of sales amounts, and then your company also run advertising on several channels. Okay, one of which is TV. You put an ad on the TV, and then you would like to, of course, this is the sale, and X1 is the budget, is an advertising budget you spent on TV. Of course, you want to explain a relationship. Okay, if I spend, for example, a million on the advertising on TV, I would like to see how much more sales increase, in the product. Okay, so in this example, you use one predictor, one variable, in order to explain the response y. After you fit the linear least square, these form a relationship, and in this example, x is just a single variable, so you can plot a relationship y and x. X is advertising cost on TV, Y is the sales. The blue dots are data sets. The red line is a regression fit. Okay, so the regression fit is, of course, is given by linear equation, so it's going to be a straight line. Okay, so in this fit, I also put beta 0, which is called intercept term. It's a constant, which is very common in applications as well. So this is the amount of the intercept term. Beta 1, what do you see? What is the beta 1 in the graph? Can you see this, Sitipak? Sitipak.
Beta 1 is the slope of this graph.
Yes, beta 1 is the slope of the red line. Okay, so basically the way we look at the problem is, okay, you want to estimate beta 1 and the slope and the intercept term so that it fits best with the data point. So it's not going to be this line, it's not going to be this line. So it's the red line that what it does is that when we talk about the residual, so the residual is the error, right? Is the error of your data point, is the distance from the data point to the to your linear model. So you're gonna measure the error, and then what you do, this error is EI, right? So you're gonna make a sum. You're gonna square it and take a summation. So the red line, the regression fit, is actually the best balance. All right, is the best one that kind of lies between all the error points in an optimal sense. And we use that optimal sense in terms of two norms. Okay. On the right hand side, if I add two predictors, if I, say my y is going to be beta 1 plus beta 2 x2. Okay. Then you have two predictors. Then the linear model forms a hyperplane. Form a hyperplane, and of course the yellow dots here are my response variables. But then the problem of linear least square that you want to find the best beta 1 and beta 2 is equivalent to finding the best hyperplane. You know that the hyperplane can all right, whether it tilts this angle, whether it this way or this way, it depends on the normal vector. The hyperplane depends on the normal vector. And then, so can you associate that the normal vector of this hyperplane with the linear regression model? Napat, can you suggest what beta 1 and beta 2 suggest in terms of the characteristic of the hyperplane? Napat?
Beta 1 is the slope in x1 direction, and beta 2 is slope in x2 direction.
Yes, but what is it called in terms of hyperplane? Ping, can you suggest? I just said, the hyperplane, the way you characterize a hyperplane is to use the normal vector. What is the equation of hyperplane again? If you have a hyperplane equation, a1x1 plus a2x2 ... an xn equals 0. This is an equation of hyperplane. This is a set of hyperplane. The normal vector is what vector? Ping?
It's the vector that's perpendicular to the plane, right?
Yes, so, but it's a vector A. If your hyperplane is described by this equation, is a vector A, the normal
it's
vector.
dot product.
Yes.
Yes, it's dot product to the x equals 0.
Right. Okay. Then, if you look at this associated with this linear regression model, all right, you will see that after the regression fit, your beta, your best beta returned from linear least square is actually the normal vector of the best hyperplane that fit best to the data points. As similar to the figures on the left hand side, if you measure the distance, you know, from each data points to the hyperplane, okay, if you measure the distance and then you this is EI, and then you square it and take the summation, that sum square is smallest when it's returned to this hyperplane. If you use another hyperplane that is not returned from the linear least square set, of course the sum square of the error would be higher. So that's the meaning of linear least square. Now I'm going to give a list of engineering applications of linear least square. These are very common example. The first one is data fitting. Suppose you have you have data points between yi and between ti and yi. You have t and y. You get basically data points maybe from experiments. Like you know, a lot of physics experiments. You measure two quantities, like time and velocity. You look at the hardware, measure the velocity, and then you collect the data points, right? And then you want to approximate y as a function of t, and you use you kind of have assumption that you should use a function gt, and then you also have a further assumption that gt can be decomposed as a sum of basis functions. All right. So common basis functions are elementary functions that, you know, when you add it up, you can use them. You can use it to explain elementary essential elements of the main functions. The common basis functions are, you know, polynomial functions. Because what we learn from calculus, all right, you can, of course, you can approximate like from Taylor series, Taylor approximation, you can approximate continuous differentiable functions by using polynomials, right? That's why the function 1t squared t to the n is called a basis function. You also learn from mathematics that you can use sinusoidal functions at different frequencies as a basis function as well. The concept of Fourier series. Okay, and there's going to be a lot more in applications like waveless functions and you know, and some more. Okay, so we leave the choice of basis function arbitrary for now, but let's assume that you have this model, and then you can form a linear regression by this. All right. So you repeat. Suppose you have I equals 1 to m because you have m measurements. First measurements, you form this equation. Okay. It's going to be y1 equals the function 1 at t1, function 2 at t2, function n at t1. Sorry, I think I said it incorrectly. Function g1 at t1, function g1 at t1, function gn at t1 times this vector. And then you repeat until m equations. Then it turns out that you form into a matrix formulation of linear least square. And of course, when m is much bigger than n, you get a tall system. You would prefer to solve it using linear least square. Okay, so the first step is to recognize that your model is linear in what? in the parameter, in the regression coefficients, whenever your y is linear in beta, okay, and that depends on your model assumption. Sometimes you come up with a nonlinear model, sometimes, you know, and so on. But whenever your output y can be parameterized linearly in beta, then it's guaranteed that you will be able to you know, write it in a linear function, linear form. So you can just form this matrix, this vector equation, and then solve it with least squares. Now let me show you some numerical examples. All right. I on the back end, I generate TI, and I generate the function values according to this equation. This is nonlinear function in T. Okay, and then the data points are given by the blue dots. All right, and then I have some assumption that, okay, I want to approximate the blue dots. Okay, and I pretend that I didn't know before that, you know, the blue dots, the data points, were generated from this nonlinear equation. All right, as a user, when I estimate the model, I'm not supposed to know this. All right, but then I have assumption that, okay, how about trying with the elementary basis function polynomials? I want to explain the blue dots by a polynomial function. But then polynomial functions, of course, it has a, it starts with it depends on the degree, right? Y equals beta 0, beta 1t, beta 2t squared, ... beta n t n tn, okay. When you use a polynomial function to approximate something, you have a arbitrary parameter, which is the degree of polynomial. All right, degree 1, you end up with the linear function. All right, n equals 2 is a quadratic. So then when you look at these blue dots, Kanatat, do you think we can approximate it well with the first order polynomial?
No.
No, because
So this has not enough data.
It doesn't have enough degree of freedom, right? So if I of course straight line, then right, if it's a straight line, it obviously you know, cannot approximate well with the data point, because the data points contain, you know, very it has fluctuation dynamics, right? So then in this example, I fit it with the 6th order, and the result is given in the red line. Okay, so then you see that it tends to explain the dynamics around here, you know, up and down. And then there's still a lot of gap to be further, some large error here. We discuss on the quality of approximation later, but in this slide, I want you to take a look at the right-hand side. On the right-hand side shows when we break down each components, because we use the 6th order. So you're going to have beta 1 x1 ... beta 6x to the 6th. All right. So in this plot, after the linear regression, we have the values of beta k fitted from solving the problem, and then you see that all these are the basis functions, you know, scaled by the fitted regression coefficients, and then of course the summation of all these color graph, the summation is the red line. So the results of data fitting is that is the optimum weighted sum of basis functions, so that the sum square error between data points and the fitted function is minimum. All right, so this is the first example. I would like to remind that this problem, data fitting, is very elementary. By now, there's a ready built-in package library in commercial software, or not even in commercial. Python, MATLAB, and R. You can just use the command to return the results real quick. Actually, even without knowing the linear least square. But then of course, in the lecture, it's important to understand the principle behind. Right. A data fitting is a category of one estimation problem. It's broader than linear least square. All right, it's a problem of fitting data points. Fitting a function to data points. Okay, some functions. If you choose some function, maybe it's not formulated as linear least square, but some can be, of course, using linear least square framework. Now, take a look at the second example, finite impulse response model. So please remind that when you use FIR model, you assume to explain relationship between input and output, using this convolution relationship, but you assume that your impulse response HK is non-zero up to degree n-1. That is why it's called finite. Okay, when you let me remind again that a user comes up with this model. Even though when we learn, the theory in the class and stuff, usually you are given, like I give you homework exercise. I told you that okay, use this equation and form it and blah blah blah. All right, but in practice, as a user, you're the one who decide what model should I use to explain, a relationship between Y and U. Okay, but once a model is decided, okay, so to recognize whether you can use linear least square is to take a look at is my YT can be parameterized linearly in terms of a parameter to be estimated. So from this equation, then you see that, okay, the measurements, the collected observable variable would be a pair of Y and T, which means this term is known, this term is known. And this is going to be parameter. Okay, and then you see from the equation that, okay, my Y is linear in theta. Then, of course, I can formulate it in terms of linear least square. So then, okay, of course, so then you see that, okay, I can write my YT equals, can someone break down this summation for me? Muhammad, are you here? Not here. Okay. Napat, okay, can you just
H of 0 and UT plus H of 1 and U of T minus 1.
T minus 1.
And
Dot,
plus
dot.
until
Last term.
H of n minus 1.
Yes.
And U of 0.
U of 0. All right. No, the last term is not U0, Napat.
Oh. T plus 1 minus n.
T minus 1 plus n. Okay. right? T minus
Yes.
plus n. Okay. So as again, you see that it's linearly in all these coefficient hk. Now, because you're gonna have measurements from you know, from different time points, right? So you could repeat, you know, repeat this equation from so it depends. Okay, if you have t from 0 to m, all right. So if you start with so you're gonna take a look at, okay, what is the index? What is the starting time index I should use? But you need to recognize that this equation, okay, on the left hand side is the response at yt. The response at yt depends on the input at previous times, right? Because in linear system, we of course, I mean, the current output cannot depend on the future input. All right, everyone see this? So it means that, okay, when you first write the vector equation, you cannot start with t equals 0, because on the right hand side you don't have the data of u at negative time index. So you're going to start at yn minus 1, right? And then yn minus 1 is going to be un minus 1 times h0 plus un minus 2 times h1 dot 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 sum with the u0 times n h of n minus 1. And then you just repeat this equation, you know, until you have used up all the measurements. Then it turns into linear regression equation, a vector form y equals x beta. All right. Can everyone do this? Like, you have linear equations and form a vector equation, but make sure you use like you use all the data points, but be careful with the starting time index. Okay. And then, of course, as I mentioned here, we didn't use the initial outputs, all right? We didn't use y0 and y1, because if you're gonna write y1, you're gonna need what? You're gonna need u1, you're gonna need u0, u minus 1, u minus 2, and of course, these inputs at negative time index are not available, right? So you need to trim out, neglect these initial outputs, right? All right. So this is it. Whenever you whenever you can formulate the problem, you know, given a model, write it into a vector form, and we're gonna explain later how to solve the linear least square. But it's very quick. It's very, you know, it's very mature. It's like it's all established. Once you get this equation, once you get the vector y and x, all right, you can get beta hat. The third example is very relevant to system identification. Now we have input, output data points, all right? But now you have questions that, okay, I would like to estimate a dynamical model that is given by autoregressive with exogenous input, ARX, okay? ARX model, the scalar one, not a vector one, is of course described by this equation. Y depends on first order lag of y. This is called autoregressive term, and it depends on the exogenous input, or of course our deterministic input. So your goal is to estimate A and B. Here then again, you recognize that your Y, your output, is parameterized, you know, linearly in the model parameter A and B. Then you recognize that, okay, it can be formed using a linear least square. So so the whole point is again formulate into a vector form, y equals x beta. Then you say, okay, I can repeat this equation. You know, I'm going to use the data points, endpoints. But then again, I see that, okay, now I'm going to start with y at time 2, because on the right-hand side, y at time t depends on, first leg of, input and output. So I'm going to start with y2, which is a y1 plus b u1. And then I keep repeating this process. Okay. All right, that's it. That's done. You form these vectors, solve with the linear least square. And one observation that I would like to give a relation to the previous chapter as well. Remember when we talk about how to choose input signal to stimulate the system, we have talked about white noise, impulse input, step input, PRBS. Okay, here in this example, you see that the sequence of U will be, when you use ARX, will be arranged in the second column of the regressor matrix X. Okay, so what happens if you use a very, a trivial signal like impulse input? What you get? The impulse input, right? You see that almost all the columns, the second column will be entirely zero. Then we're gonna see later that, okay, this makes some property on the regressor matrix X, and that makes the problem hard to determine a beta. And that makes sense because impulse input doesn't give any information to stimulate the system. You put zero almost all the time, right? You put zero all the time. How are you gonna get rich information from the output signals that allows you to estimate the model? Okay, here's the result. Okay, when we get data points again, I generate data points according to ARX model. This is the true parameters. A equals 0.8, B equals 1. When I generate the data points, because this is ARX, okay, when I put some values on Y, do we have restrictions on the value of Y so that this system is stable? This system is stationary? Sitipat?
stationary ครับ
If
if
condition on A. Do we have some condition on A?
A ต้องมากกว่า0หรือเปล่าครับ
This is discrete time. This is discrete time linear state space equation, right? Right? It's actually fit into this form, all right? We know that what condition under system parameters A and B that make this linear stochastic model stationary? Depends on A or depends on B?
A ครับ
A. Okay, what is it? What is
A
that?
A is stable.
Yes, and that big A, I mean, this just a scalar system. So this big A plays the same role as this small a. So this small a has to be
less than 1.
not less than 1. The magnitude must be less than 1, okay? So this, I mean, of course, I want you to associate it with the theoretical results with the experiment all the time, because in this experiment, I need to generate data points, right? When I generate data point, it means like, okay, I come up with a ground truth model, but that ground truth model has to be stationary. So when I choose the two parameter, I cannot choose any arbitrary of A and B. I cannot choose A equal 1.2 because your data points will not have stationary property and unstable actually. All right. Okay. Get back to our main idea. I generate the white noise to perturb, to corrupt the measurements. Is a white noise with variance 0.1. I use PRBS input, okay, with 2 levels, -1 and 1. If you look at the output, the blue dots are the actual output. The green dot are the estimate. The green dots are y hat from the estimate. So the estimated parameter after I solve it is 0.75. B hat is 1. So you see that we're gonna discuss about, you know, how can you discuss about the quality of estimator later, but this is just to get some, like, get you to see some example results first. That okay, the true parameter is 0.8, but what you get is 0.075. Is this a good estimate? Do we get good estimate like this example all the time? What are the factors? Okay, we will talk about that later. Okay, you should be convinced that in order to get y hat, right, you just use the what? You just use the parameter estimated from the least square and replace in the equation like this without the noise term when you produce the estimate, right? Because the noise term is the undesirable term. Actually, we estimate A hat, B hat in order to make the sum square error minimize. So when it comes to the estimation process, so I use this green box equation in order to produce the green graph, the estimate. Okay. All right, that's a basic example. I give you 3, but now it comes to the in the next slide, I will explain how to estimate the model. Okay, what are the mathematical forms? But I would like to break the video for now first, so that it's not that long. Okay.